You probably already know how to add and subtract fractions. But why does that procedure work? You probably know that you need to find a common denominator, but why exactly do we multiply both the top and bottom by the same number in order to change fractions? How would someone have figured out all of this to begin with? Let's find out here on Inductica. We return to our hero Bar, who has been inventing fractions and methods of manipulating fractions in order to gain an edge in his business transactions. Bar has been selling, for example, partial sweet cakes. Instead of having to sell the whole cake all at once, he's able to sell fractions of them. But he finds that at the end of the day one day, he runs into a bit of a challenge when he is trying to figure out how many sweet cakes he has left. At the end of the day one day, he has one group of 5 sweet cakes, another group of 2, but then he has a 1/6 slice of sweet cake and a 1/3 slice of sweet cake. So this leads Bar to this following question. How does one add fractional quantities with different unit sizes? Or similarly, how does one add fractions with different denominators? So Bar is trying to understand this particular problem. The rest of the problem is obviously easy, it's just adding. And the real challenge here is that he has units of different sizes. He can't just add 1/6 to 1/3 and say, oh, it's 2 of something, because the sizes of the units are different. Now, from a previous induction displayed on the screen, Bar knows that he can actually change the unit size of a fraction by dividing both the top and bottom. So as a result of this, he realizes that he can actually change the unit size in a different way by multiplying by both the top and bottom. Let me show you how he figures this out. Bar realizes that all he has to do to make these units of the same size is to chop the units of the 1/3 sweet cake each in half, since that will give him units of 1/6. But how exactly does that work mathematically? The way he can figure that out mathematically is that because each of the units that were present were split in 2, that's the same as multiplying the top, which represents the number of units, by 2. As a result of this multiplication by 2, the piece sizes are now twice as small. It takes twice as many of them to make a whole. And so as a result, that requires Bar to multiply the bottom number, the denominator, by 2 as well. This leads to a change in the problem, which looks like this, and now the problem is very solvable. It's just regular addition. Then he gets 3/6 for his final answer, which of course, through a previous induction, is simplifiable to 1/2. As a result, Bar is able to reach the following conclusion. To add 2 fractions of different denominators, multiply the top and bottom of one or both of the fractions by some number to get a common denominator. Then add the numerators of the resulting fractions. Motivation 2. In a different case, Bar has 2/3 of a sweet cake left, and someone comes into the shop wanting 1/4 of that partial sweet cake. Bar then immediately realizes that in order to figure out how much of a sweet cake he has left, he's going to have to figure out how to subtract fractions. So that leads Bar to the following question, question 2. How does one subtract fractional quantities with different unit sizes? Or how does one subtract fractions with different denominators? Bar once again realizes that the reason this problem is difficult is because the pieces have different unit sizes. It's not clear, you can't just do 2 minus 1 again. They're of different sizes, so it's not immediately obvious how you're supposed to do this. But once again, he realizes that he can use the same trick as last time to make the unit sizes the same, and then he can simply subtract along the top. So how is it that Bar can get different unit sizes? Well, he guesses and checks a little bit, and he realized that what's going to end up working is if he multiplies both the top and bottom of 2/3 by 4 and multiplies both the top and bottom of 1/4 by 3. Now, just by way of demonstration, let's understand why exactly we need to do this again. So he's trying to get a common denominator of 12. He realizes that's a way he can split all of these so that you actually get 12ths, so that they have the same unit size, so that they can be subtracted. And so he's splitting his 2/3 each into 4 pieces. Okay, what's that going to look like? 1, 2, 3. Okay, yeah, cutting 3 times gives you 4 pieces. So this 1/3 got split into 4 pieces. And then this other third over here also got split into 4 separate pieces. Okay, now let's draw a hard line there between the 2 thirds. Each of these 2 thirds got cut into 4 pieces. So as a result, the 2 pieces got multiplied by 4 because for every piece, you now have 4 pieces. So it's 2 times 4. Now finds the number of pieces. Because each of these pieces are now 4 times smaller, it takes 4 times as many of them to make a whole. And that's why it's valid to multiply the bottom by 4 as well. You don't want to make a shortcut, an inductive shortcut. I mean, this is fine if you understand it, but if you're trying to do it inductively, you can't make the inductive shortcut of the following argument, which is common. Oh, I'm just multiplying by 4 over 4, which is 1. And if you multiply by 1, then that's fine. Yeah, so like that's mathematically valid, but our goal is to understand this actually in terms of the reasoning about actual physical objects that would have led to these methods. Barr would not have just jumped to this kind of reasoning. And even then, it's reasoning that is not directly connected to the observations, which is what we are looking for. All right, let's carry on to the changing of the 1/4. This 4th is split into 3 pieces so that it can make 12ths. All right, and as a result, that 1 piece is split 3 times, making 3 pieces. And each of these pieces is 3 times smaller, which means 3 times more of them are required to make a whole. And so we multiply the bottom by 3. Remember, the reason for this is because the bottom of a fraction represents the unit size by telling us how many of such units are required to make a whole. This converts the problem into 8/12. This converts the problem into 8/12 minus 3/12. And now that he has a common denominator, he can simply subtract, yielding 5/12. Barr now knows he has 5/12 of a cake remaining. Conclusion 2. To subtract 2 fractions of different denominators, multiply the top and bottom of one or both of the fractions by some number to get a common denominator. Then subtract the numerators of the resulting fractions. So that is the observation-focused way of thinking about how someone could have developed systems for adding and subtracting fractions. Join us next week as Barr discovers a way of splitting up the profit from an investment using the multiplication of fractions. I'll see you then. This video is part of a longer series dedicated to reproving the essential ideas of math and physics by showing an actual process of observation and reasoning steps scientists could have taken to prove these conclusions. Observational proofs, also known as inductive proofs, give us a deeper, reality-based understanding of these abstract ideas and demonstrate the proper method of scientific proof. This series starts with cavemen counting rocks and will continue all the way to the frontiers of quantum and relativistic phenomena. This epic story will proceed in a possible order of discovery, since science always progresses by reasoning about observations using what has been discovered earlier. To discover the long-term goal and the true power of this project, visit my channel page for more information. To see the playlist for this series or to see my channel, just click on the links on the screen. Finally, if you'd like more lectures like this, just go to patreon.com/Inductica. For just $5 a month, you gain access to the written, rigorous forms of these proofs, as well as my 34-hour lecture series, An Inductive Summary of Physics. I'll see you in the next video as this inductive journey continues.